Hello, this is Dr. Daystorms, and we're now starting Chapter 2, which deals with atoms, molecules, and ions. And so we're going to start to really delve into what is really the underlying concepts of chemistry. One of the first important people in the history of chemistry, at least, is John Dalton, and he came up with the idea of atomic theory. Within atomic theory, he postulated the following. He postulated that the elements, that were known at that time at least, were all composed of small identical particles, and he called these atoms. And that, for example, the element of, nitrogen or fluorine or oxygen or anything like that, or carbon, let's just say carbon, were the same, were going to be were identical. They would have the same properties, whereas if you changed it just slightly, it's no longer the same atom, it would be a different element. Okay? He also stated that compounds are made up of different atoms, but they're always in the same relative numbers, and this is really important later on in just a moment. We'll talk about that. And finally, he postulated that whenever you have a chemical reaction, you just rearrange the atoms between the molecules that are reacting, but it doesn't create or destroy them. This is really a play on something that the French scientist Joseph Proust had proposed, which is called the law of definite proportions. And so what he was saying is that any time that you have a given compound, whatever that compound may be, so for example, here I'm just showing carbon dioxide, it's always going to contain the same elements regardless of the location, and in the same mass ratio. So for example, if you take a sample of carbon dioxide from here in Florida, the ratio will be 1 carbon to 2 oxygens. If you go to Mexico or you go someplace else, throughout the world, and you take a sample of carbon dioxide, the mass ratio, once again, will still be 1 carbon to 2 oxygens. So this is the law of definite proportions. Then there was the play on that called the law of multiple proportions, which just means that if, for example, carbon dioxide, but you can also take a carbon and hook it up with a single oxygen, carbon monoxide, and it also, not only does it have the same mass ratio for all carbon monoxides, but it's a whole number difference, an integer difference in the mass ratios between carbon monoxide and dioxide. So it means that, for example, carbon monoxide only has 1 oxygen, but all carbon dioxides would have 2 oxygens. It's a whole integer. And the third portion of Dalton's atomic theory really leads to this idea of the law of conservation of mass, which means that the total mass of a substance at the end of the chemical reaction has to be the same mass that you started off with. And so in this example here, I was just going to show you, we've been talking about electrolysis and how you could combine hydrogen and oxygen to make water, or break electrolysis was breaking water apart to make hydrogen and oxygen. But if you notice here, you start off with 4 hydrogens and 2 oxygens, and ultimately, even though you make 2 water molecules overall, you still have 1, 2 oxygens and 4 hydrogen molecules. You didn't create, we only have 1 creator. We didn't create a hydrogen or lose a hydrogen somewhere along the way. Then as time went on, other scientists started to consider the idea that the atom could be broken apart into smaller particles, I should say. However, it's no longer has the same characteristics. Sorry about that. It no longer has the same characteristics as the atom itself. So, an experiment was done that if you screened they discovered the electron whenever they screened the particles through a charged magnetic field, and lo and behold, the negative parts went towards the cathode tube, and so therefore this proved that there was a negative portion of the atom itself, and so this was called the electron. And that comes from J.J. Thomson, by the way, around 1900. So Thomson then came up with the idea, here, actually I want to go on. Thomson came up with this idea that he called the plum pudding model. And so I wanted to include a picture of plum pudding. And this idea was that you just had this positive charge in the sphere, and you had these discrete negative electron packets, sort of like you would have a pudding with the plums in it, I guess. I've never personally eaten plum pudding. But that was around for a few years, and that was called, many times it's called the Thomson model was often called the plum pudding model. Around the same time, we also had the idea that there's radioactivity, which is that there were certain atoms that would spontaneously shoot out other particles. And later on, we're going to find out, next semester, we're going to actually discuss radioactivity and nuclear chemistry in greater detail, where we talk about like neutron emissions and alpha particles and things like that. But Henri Becquerel was one of the first to observe it, but then perhaps more famously, this was studied by Marie and Pierre Curie. The way that the plum pudding model was discredited was done by Ernest Rutherford. He shot alpha particles, which are essentially helium molecules, at a really thin piece of gold foil. And lo and behold, it just didn't go, like the alpha particles just didn't go right on through, and they also just weren't just evenly distributed all over. They were just scattered at discrete points. And so let me show you a different picture of that to try to get the idea across. So what happens is you do have some of the molecules that would just go right on through and they'd hit the fluorescent film on the back side. But then some of them would hit something and ding off at a very specific angle. Okay, another one barely hit and ding this way, or would be dinged at these discrete angles. So that meant that there had to be something more solid in the middle, or there was something more solid than just this electron that would go through, okay? And so it wasn't like the plum pudding molecule. And so what came out of that was the idea that we have what's called the nuclear atom. And so Rutherford was postulating that we have this very small, dense nucleus, and that the electrons are essentially like an electron cloud that's outside the atom, and that's the vast majority of the space of the atom. So if you imagine, we have our neon sign here, which are individual neon atoms, and they're bouncing all over. But if you look at just a single neon atom and you blow it up, it has a very, very, very tiny, dense nucleus, which I can't even do it justice. But here the relative size in angstrom or an angstrom is 1 times 10 to the minus 10 meters, and the nucleus is 10 to the minus 4 angstroms. Okay, so then, that's like approximately about 1/10,000th of 1 times 10 to the minus 10 meters. So it's ridiculously small, whereas the entire atom itself is roughly 1 to 5 angstroms. And so that's the vast majority of the space is that electron cloud, and you have this very tiny nucleus. We're going to then talk about what's found in the nucleus. Okay, so most of the volume is empty space. So then there were other subatomic particles. In 1919, Rutherford then discovered protons, and protons are positively charged. And then we have Chadwick coming along a few years later, in 1932, discovering neutrons, and neutrons are neutrally charged. Okay, and so this is what's very important, this part right here. Protons and electrons are the only part that are charged. Okay, so a proton is positive, an electron is negative. Neutron is neutral. It's easy to remember its name. However, if you notice, a proton and a neutron have about the same mass, but an electron is ridiculously small. It takes like around 1,800 electrons to equal 1 proton in mass. But since all of this is really tiny, like, a proton weighs approximately 1.66 times 10 to the minus 24 grams, it just makes it too difficult to discuss its mass of a single atom. For example, a hydrogen only has like the regular hydrogen atom, would only have one proton and one neutron, and so we would be talking around something around 3 times 10 to the minus 24 grams for mass, which is just ridiculous. So instead, they came up with this own mass unit called the AMU, or the atomic mass unit, and so one proton approximately equals 1 AMU, and one neutron is equal to about 1 AMU. But if you notice, even then, the electron is 5.5 times 10 to the minus 4 AMUs, essentially. And so we don't usually, we really won't include or need to include the electrons, because it's not possible for an atom to have so many electrons that it is significant in its mass. So the mass of an atom can be based off of the number of protons and neutrons that it has. So I hope that this has helped explain the parts of an atom, or at least begin the discussion on the parts of an atom. I'll see you in class.